keep stuff going. But let's hit this, go back. All right. So, and then at the end there'll be a little sign out sheet, just lets you give me feedback and then also lets you ask for certain topics. So we have access to a lot of speakers across the road at all the different companies. So if there is a topic you specifically think someone over there might be able to speak to, feel free to let me know and I'll do my best to find a speaker for you. So this night's talk is a follow-on talk to one that was given, I think, towards the start of 2025, so last year, and that was Introduction to Electronic Warfare, where it was a broad survey of all the techniques, the various facets of electronic warfare, whether that's electronic support measures, countermeasures, countermeasures, that kind of thing, and then specifically went into some of the techniques under each subcategory. As I said, I have a form that lets me get feedback, and from that, I saw that most people were specifically interested in the target-like jamming / deception jamming techniques, which I agree with. So I decided to give the follow-on specifically focused on that, just so we can kind of spend the requisite time needed to give you guys a better understanding of how most military electronic warfare systems and modules are operating nowadays, which is through this technique. And we'll discuss a little bit as to why this is more valuable than, let's say, barrage jamming or spot jamming. Although those techniques are still used, they have their place, but specifically against very advanced integrated air defense networks and systems like that, deception jamming is by far one of the more superior tactics at play. So that's the sign-in sheet. So real quick intro for those who haven't seen me. I see a lot of familiar faces. It's good to see we've got some recurring guests. But so my name's Ethan Hoban. I'm the president of our HKN, which is our Eta Kappa Nu chapter here at UH. That is the IEEE Honor Society. So for those of you who are electrical or computer engineers, if you meet certain criteria, you get an invite from me to join the society. And there's a bunch of benefits. I won't go over them here, but it's a good idea to join. Currently, I'm a full-time Tempest engineer at Northrop Grumman. I graduated from the UH Electrical Engineering program back in 2023, and currently working on a master's, doing my thesis now. Hopefully we close that out by the end of the year. And then in addition to my full-time job at Northrop, I have another job at Northrop. And then in that one, I do a lot of stealth electronic warfare stuff. Fun gig, newer one. Habitual project collector, you can see some of the stuff I get up to. eBay's your friend. I assure you of that. And then rocket enthusiast, can't be a rocket city without launching off some rockets. So, what to expect from this talk? I just broke this down more specifically in the slides themselves. But there's gonna be a quick disclaimer. Obviously, I'm a cleared employee, I work across the street, so we're gonna hit some ground rule stuff. There are some things I won't say, and anything I do say, I have cleared from entirely unclassified open source information. There will be no compromises today. We're going to do an overview. So for those of you who weren't able to attend the original talk or just aren't as familiar with the topic matter, we will do a quick overview of electronic warfare. We will quickly discuss the various facets and subsections of electronic warfare, and then like the broad concept, what is it? You know, is it cyber warfare? No, but you know, that kind of thing. Quickly, types of jamming, then we're going to lock in specifically on target-like jamming, the concepts, the techniques, that kind of thing. So here's our disclaimer. I assure you this is all unclassified. Most of the information is all unclear, or is all open access. The main source of information for this one is a text by August Golden Jr., Radar Electronic Warfare. It's an AIAA education series text. You can find it online for free. You can also buy a hard copy for about anywhere from $40 to $70 used on eBay. It's a very good book. I recommend it a lot. And it has more than just this. It has quite a lot of information that's very helpful. And then, big thing. This is one of the topics that you can actually very easily experiment with at home, which is why I have to put this one in here. Don't. Jamming is illegal everywhere in the United States. It's even an issue for the government. They themselves have to go through a lot of paperwork to even be allowed to turn on a jammer. It's not easy. The FCC might show up at your door, but your local ham radio people will absolutely show up at your door, and you will not have a good time. So keep that in mind, and that goes for any radio. You can purchase a bunch of radios on Amazon. That doesn't mean you're allowed to press the button. So, a quick overview. Broadly, electronic warfare is any system that makes use of the electromagnetic spectrum to negatively impact adversary systems. When we say adversary systems, that could be radios, radars, anything like that, receivers, anything that uses electromagnetic waves to communicate, sense, measure, what have you. So a common type of electronic warfare, not the only type, but the most common type is jammers specifically. And then obviously jammers can do a lot of different things. But I mentioned that there's 3 categories of electronic warfare. Those are electronic support measures, electronic countermeasures, and electronic countermeasures. An electronic support measure is the rock, the basis of all other electronic warfare techniques. Often, in order to execute a successful electronic warfare attack, you need information about your adversary. That is gained via electronic support measures. Surveillance receivers, intelligence gathering assets like jets, satellites, those types of things. The United States is one of the world's largest, actually not one of, the world's largest electronics support measure and electronic intelligence collection group. Everything we know is done via collecting mass quantities of waveform and signal data all the time, all over the world. If you guys have ever seen, large facilities with a bunch of circular radomes, it's very likely that it's an ELINT facility. And often those radomes are connecting to satellites in space for downlink. Electronic countermeasures, that's what we're going to talk about today. This is the official name for electronic attack measures or electronic countermeasures. You are countering your adversary. So obviously jamming, all those types of techniques. And then the next one up is ECCM, electronic countermeasures. This is the opposite. If someone is hitting you with electronic countermeasures, ECCM, electronic countermeasures, is meant to defeat that. A very common method for that is called spatial processing in the radar world, which is where you adapt your array pattern to place nulls to block out noise. We'll talk about that a little bit more because I do have some stuff regarding antenna patterns that actually is rather important. So, real quick, for anyone who does not know or has not seen the electromagnetic spectrum, just wanted to show this off real quick. When we're talking about electronic warfare, normally that just means we're isolated to these bands. So really generally I like to say 1 millimeter to 1 meter, although it can go lower, which basically means 300 gigahertz all the way back to 300 megahertz is our frequency band for the microwave region. And then there's a long range region where it goes lower, like 100 meg, down to kilohertz. In the modern age, you tend to see a lot more high frequency stuff. There is a lot of lower frequency things that can happen, such as over the horizon radars in the hundreds of megahertz. But those already have relatively low resolution, so they're not a massive threat compared to like an X-band or an S-band fire control radar. That's in the 2 to 4 or the 8 to 12 gigahertz region. So this is just a broad thing. I will note, you could technically call it electronic countermeasures because the visible spectrum and infrared and ultraviolet are here, and we have methods to do infrared jamming, that kind of stuff, UV jamming, spectral jamming, that kind of thing. We're not going to cover that here, but just know that that exists. Like we do outfit planes with anti-infrared systems. That is a thing. So, as I said, we're focused in on ECM today, so electronic countermeasures. We're talking jamming. ECM is broken down into this chart, where you have active and passive systems. When we talk passive, we have things like clutter enhancement and observable reduction. Clutter enhancement means you increase the relative signal to noise ratio of your area. If a radar tries to look at you, you're trying to send back a bunch of random nonsense. A very obvious or a very common example of clutter enhancement is things like chaff, releasing large amounts of reflecting, small dipoles like aluminum, that kind of thing into the air. So instead of them seeing one very obvious plane signature on their radar, they instead see one very large cloud of chaff, and they can't exactly locate you or any other assets within that area. Clutter enhancement, very common for naval assets. Observable reduction, this is stealth. Lowering the radar cross-section of your vehicle, whether that is through RAM coatings, geometries, what have you. Any observable reduction is a passive ECM technique. Active is where we're going to be sitting today, where we have noise-like jamming and target-like jamming. Noise-like jamming is barrage, spot jamming, where barrage jamming is focusing your jamming power into a large chunk of the spectrum, try to block out multiple frequencies all at once, where spot jamming is pick out a specific frequency you're worried about and block that one specifically. Very common, if you look to like the Ukraine scenario kind of stuff, barrage and spot jamming is one of the most prolific ones you see. That's the reason they had to come up with fiber drones. Most commercial drones use 2.4 gigahertz as their command signal. So that means you just focus all your jamming energy to 2.4 gigahertz, and technically they shouldn't be able to fly. Now, there are ways around that. You just switch frequencies. And they did that for a little bit, but then, it's not hard to measure that there's a new frequency at play. You just switch your jammer, and then they're like, all right, let's just, make webs of fiberglass all over the place instead. And it worked out pretty well. Target-like jamming. That's where we are, and that's what we're gonna focus on today. Basically, for target-like jamming, it's a lot fancier. And fundamentally, the point of target-like jamming is, let's say a radar is looking at you, and it sees a blip, obviously, and you're the only blip that's there. With an advanced target-like jamming system, you would be able to make it look like you are a different plane. Let's say you're an F-16, you could make yourself look like a B-52. You could make it look like there's multiple planes in different locations, at different speeds, at different sizes. All from your own location. There's no other assets assisting you here. You can do this entirely on your own with advanced signal processing techniques, which we're going to go over in a bit. This is extremely important, and I'll mention this a bit more, but noise jamming against a radar, the second you blast a bunch of noise at a radar to degrade its performance, that's immediately detected. They'll know something's wrong because they know what the normal noise environment looks like. They get what ambient looks like. So they'll know someone's coming immediately. So you've already given yourself away right there. Additionally, if it's just noise jamming, guess what? They can locate where the noise is coming from. So you've also just given yourself away. We have systems, we and also adversaries, have systems called HARM systems, home on radiation missiles. They're used for counter radar, counter jamming, basically. They have seekers, which are just passive antennas, and if I'm radiating, they will pick that up and fly towards me and hit me. So jamming, from a noise-like perspective, is not always preferred because you give yourself away multiple ways. And also, of course, it doesn't really stop them from finding you because they can home in on you. Additionally, there are a lot of techniques that can actually deal with noise-like jamming, like the spatial processing I mentioned, but there's things like side-lobe blanking and other techniques that are able to drop the noise for long enough for them to see an actual ping that they can then fire on. Target-like jamming does not have such an issue because they don't know who's who, which means they have to fire on everyone. So, this is, I took this from a thing about pulse compression, but it does let me illustrate the point to a certain extent here. When you're doing noise-like jamming, your objective is to take this level of magnitude from the overall just frequency domain and kick it up to the point where any spike, these spikes would be target spikes, if any spike occurs, but the overall noise level is above it, technically, they can't see you. They don't know you're there, they just know that obviously someone's jamming them actively, but they can't tell as their radar sweeps if you're there, they just see a bunch of noise. But, of course, as we said, you're just emitting a signal that lets them guide right to you. When you see something like this, this could be a target signature. High resolution radar hits you, and then you get a couple large diffraction returns back. This right here obviously shows that there's someone there. But with a target-like jammer, you could introduce extra target spikes in different locations, magnitudes, different times. And by doing that, they could still theoretically see that you're there, but also they're going to see a bunch of other false targets. These false targets are exceedingly difficult to discriminate against. It can be done, but it takes time. And when you're fighting, time's rather important. When your intercept window is on the order of minutes, maybe seconds, if I confuse your radar operators for 10, 20, 30 seconds, that might have bought me a win right there. So it's far more common, and as you could probably imagine, far more difficult to deal with. It's extremely hard to discern between a false target and a real target. So when I say this thing like target-like returns, what does that really mean? So back here, If it's a older radar without a lot of fancy bells and whistles, a target return could very well just look like one large magnitude spike. And just be like, okay, there's something here. But modern systems are of the high resolution variety, which means we can gather more information about a target when we send a radar signal on it. If this system were worse, so this right here is the radar pulse. So it hits it, and you can map these points to different magnitudes as the radar goes over the target. And basically what it means is you can fingerprint something based on your viewing angle and say, oh, this is I think that's an F-14. Yeah, this is an F-14, that kind of thing. If it's a lower resolution, like we saw with just a single spike, it just means it doesn't have enough resolution to resolve that there's multiple feature peaks here, and all of these condense into just one spike. That's an older system. This is a higher quality system. This is how we do things like identify exactly what kind of aircraft it is or missile that it is on the fly. We've already done, as mentioned, electronic support measures. We've collected this information ahead of time, programmed it into our radars for discrimination purposes, and then when we see these fingerprint returns, we can say, oh, that's an F-14, that's a Tomahawk missile, whatever. So our objective from a target jamming perspective is if we see a radar signal hit us, we want to generate fake fingerprint signals and send it back to them. It sounds simple, but unfortunately it's not quite that simple. And we'll get into a little bit as to why shortly, but just know the broad concept here is you wish to inject false information in the form of these high resolution profiles back to an offending antenna who's looking at you. And ideally you want to do it very, very fast. As we've been speaking about, the perspective of a radar, generally, is it sees a blip with a position and a speed. Most modern systems can see a decent amount more. They can identify targets based off these fingerprint parameters. Most often, as we saw with the F-14 image, it's related to their geometry. So the physical shape, size, coatings, that kind of stuff on an asset is going to directly result in a fingerprint that you can just tie to it. Radars have very limited ways to discern between their own signal reflecting back and a radio signal intentionally transmitted towards it. All a radar is a radio that sends out a pulse, the pulse hits something and reflects back and it's waiting to listen. Now modern systems have things like pulse coding and they have things like, they focus on coherence. So when I say pulse coding, they can do things like basically put information and stuff like that into the waveform such that they know which pulse is coming back. Because let's say you're a continuous wave radar, so you're sending a scanned beam, and as you're scanning the beam, there was a target very far away when you just hit that scan. But then as you went over, as this return is coming back, you hit a target that's super close to you. So the return that came later comes back first. By coding information into the pulses, you can catch that. And that'll prevent things like errors and mixing up what's going on. Because generally you would expect, if you didn't have any data, that the pulse that came back first was the one you sent out first. That's not a guarantee. So it's important to be able to, yeah.
So that means like changing up the frequency it's sending out somehow?
Yeah, so they can encode things. So let's take, for example, an FMCW, frequency modulated continuous wave radar. You can change the chirp signal. You can, swap the chirp. They can actually physically encode actual bits into it if they wanted to. Doing that kind of stuff, though, risks, there's waveform issues. You gotta very specifically pick your waveforms. So it depends on the radar, but often what you'll do is you'll just encode a specific chirp or something like that in. So as you're scanning, they've done studies where they can basically say, what is the likelihood of this scenario? Because again, these are moving at, it's electromagnetic waves are moving at light speed. So there's only a limited window for that whole return jumbling to occur. So technically you could do some math and be like, how many chirps do I need to be able to rotate through in a given time span to guarantee that this doesn't happen, or at least be like 99.99% sure. So you can just swap between your chirps. Okay. And the chirp is just, does everyone know what I'm saying when I say chirp? It's fine if you don't. You've definitely seen it. You've absolutely heard a chirp before. When it's so everyone knows what a sine wave is, just continuous frequency, it doesn't change, it's a fixed frequency and then just oscillates. A chirp is it could be a sine wave, it could be anything, but really any signal that starts at a frequency, and as it goes through the time domain, the frequency increases, decreases, what have you, so it starts getting super compressed in. So basically, imagine a chirp going whoop. That's the noise that they sound like. It's actually very helpful. They use chirps in a lot of things. It gives you like this broadband selection of bandwidth, which it also means it gives you more frequency responses because radars and radar cross-section is dependent on different frequencies. So they'll have different responses based on what they're hitting. So chirps are very common. And more broadband chirp just means you have a better radar. But using this concept of sending intentional false data, yeah.
So when you swap between chirps, are there certain frequencies that are preferred over others?
Depends on the radar and depends on what you're looking for. Obviously, you want to stay within your band most of the time. They have things like ultra-wide bandwidth radars, but almost always you're going to stay, like let's say X band. You're going to sit at like 10 point something gigahertz, and your chirps are often only going to be maybe a couple megahertz wide, and all it would mean is like chirp 1 is 1 to 2 meg, chirp 2 is an additional 2 to 3 meg, that kind of thing. So you have these distinct blocks where the frequency is slightly offset, so you can tell who's who as you're talking. Yeah, and then using this concept, you can generate false targets, rather realistic ones too, where I'm just intentionally sending back fake data. But as we said, they could switch up the waveforms rather quickly, and these things are moving at the speed of light. So there's not a lot of time from when it hits me. It's already heading back, so once it hits me, I have to start processing and planning to do something, and then send it back. So the answer is, unfortunately, they'll get a return back immediately, eventually, and then yours will follow up after, just because of the physics at play. You can't preempt something unless you have exceedingly good electronic support measures, which means you already know what's there. So you can fly in already faking things, which is very common. So if the radiated jamming signals are similar to the signals scattered by the target, this is what we call target-like jamming. So as shown with that F14 image, if I was to play back a signal with the relevant frequency, amplitude, polarization, all those parameters that had those spikes and sent it back to the radar looking at me, the radar would have a high likelihood of saying, that's an F14. I could be a B for all I care. It's still gonna think I'm an F14 most of the time. There are ways to beat this. And then since this target-like jamming signal can be identical to radar returns, they can't improve their signal to noise ratio by integrating many pulses. The reason I say this is normal jamming, and I'm sorry, jamming to signal ratio. Normal jamming, like just noise jamming or barrage jamming, if you integrate a bunch of pulses over time, the target can slowly come up out of the noise, which means there's a way to get past the noise issue. With this, it doesn't help you because the target and the false target both will come out of the noise at the same rate. So it doesn't improve their ability to discern who's who. So now we're going to talk about the methods and parameters that you can tweak within a signal to actually result in different types of errors or deceptions in the radar. So the biggest one and the easiest one to do, you can actually do this rather simply with normal parts like RC circuits, LC circuits, that kind of thing, which is time delays or advances, but generally time delays. Obviously, as we know, the radar sends out a signal, it reflects off something and comes back, and it uses the time of flight to determine range, how far away something is. Well, if you capture the signal, hold it for a second longer, and then send it back, they'll think you're farther away. And this is the first part of generating a false target in a different location than you are. So you're here, signal comes in, you catch it, and you send back a fake signal. Or more likely, you already know what they're going to use signal-wise, so you come flying in, emitting this fake signal from the start. And when you do that, they're going to think you are farther away than you actually are. But again, the way radars work, modern ones, is they're scanning array radars. So they're using beam forming to basically generate an electromagnetic laser that they can scan specifically with. So when they get a return, they have an associated azimuth and elevation. which means they can triangulate and get a 3D position in space. So by messing with range, they still have the azimuth and elevation, so they know where, but you can play with if you're closer or farther away. That's the first step. The next thing, we're all familiar with Doppler shift. You know, if it's coming towards you at a higher speed, frequency compresses and increases. If it's going away from you at a speed, frequency drops, right? Doppler shifting is how we get the velocity of a target. It's a very common method of discrimination. Often, modern stealth vehicles will have radar cross-sections comparable to insect swarms, birds, that kind of thing. Which means, technically, I don't expect to see a bird flying at like 40,000 feet. But if it were to occur, an easy way to tell, is this a bird or is this an F-35, is how fast it's going. If the bird is magically at 40,000 feet, it's definitely not going to be at like Mach 2. So we'll be able to catch that with the Doppler shift. But what did we say the Doppler shift fundamentally is? It's a change in frequency. We could do that. We can introduce false velocities, false speeds, by modifying frequencies or phases, but generally frequencies. So if we expect them to send a 10 gigahertz signal at us, and we want to introduce, some Doppler shift and say, oh, we're like a Mach 3 missile, well, we can go back and send them like a 10.2 or something. I don't know the specific conversion in that case in my head, but you would send a higher frequency back, along with maybe this time delay, and they're going to see a faraway target moving very quick, even if you're moving slow. Because the important thing here as well, the radar equation shows us that, obviously everyone knows the inverse square law as it goes, drops intensity is the 1 over squared type thing. Well, let's think about how a radar works. It does that, reflects, and then does it again, which means it drops 1 over to the 4th power, 1 over range to the 4th power, which means it drops off very quick. This energy goes away very, very fast. Often when the radar receives something, it's in like the nanovolt, picovolt, microvolt range, very small. Which means this is actually something a lot of people might not get. For barrage jamming and noise jamming, you often need really high power transmitters in order to effectively block out and raise the noise of everything. For something like target jamming, you don't. Because what's the point of having this super high power transmitter when you know that their return signal is already going to be on the order of like microvolts, microvolts, nanovolts, that kind of thing. Which means you can get away with like 1-2 watts of transmission power. Because guess what? You're only sending it in one direction. It's not bouncing back to you. You don't care about that. So your energy only drops off 1 over r to the square instead of to the 4th. Which means you don't need that much power. Which means you can have very small platforms that are extremely capable. And we'll talk about a very popular example towards the end of the talk. But by playing with frequency, you can introduce a false velocity, false speeds. So far, these two operations are very simple to do. You can do these, you can absolutely do time delays entirely passively. They'd be fixed, but you can absolutely introduce it with a delay network, an LC delay network, what have you. Frequency and phase shifting, a little trickier, but you can still probably do it rather quickly. Amplitude, this can play with angle. And the ways it plays with angle is interesting. So again, so far we've said we can change how far away we are and we can change how fast we're moving. At least that's what the radar thinks. Obviously, the next thing we want to do is move ourselves away in space, because if they still have us on relatively some type of line and at some type of speed, they're still pretty close to us, a little too close for comfort. So we want to move the false signature away from us physically. This also aids in being able to produce several false signatures in various locations to create a cloud of threads. But for amplitude and polarization, you'll notice the error, also in multiple sources, but they work similarly. The error is created in angle. When we say angle here, we're talking about the azimuth and elevation, basically the aspect angle that the radar is viewing, like where it's physically looking in space. The way amplitude and polarization do this is a little funky. And let me see, is my next one the image? I need this picture, okay. So this is a linear antenna array pattern, just from a simple calculator online. I think this is like 20 elements. And basically, when I said that whole electromagnetic laser thing, basically, if you just have a bunch of antennas in a row, just all lined up, spaced about half a wavelength apart, and you feed them all with the same signal, just power split equally across all of them, same exact signal, your pattern is gonna go from one antenna, where it would have just been a lobe, just a single, hemisphere. And as you add more elements, you get this narrow beam forming because of constructive and destructive interference. They slowly shape up. We'll notice that, so from this thing, what I'm trying to say here is, the higher we are, the better we're receiving. It means basically imagine that if a signal comes in here, it will be far higher in level from a measured perspective than if it comes in from this side. So this is basically an attenuation. Very minimal attenuation, significant attenuation. And that's on purpose, because if you don't have significant attenuation in those side lobes, a signal can be introduced in there and there'll be an error. Guess what we're gonna do? That. If I want to create a false angle, I want to use amplitude. What does that mean? Just increase the power level of the transmission. Except, let's say I have a watt of power. If I send a watt of power into this lobe of the radar as it's scanning, let's say that has 0 attenuation. It receives a watt. That's not true, but let's just say it is a watt. Well, if I send a watt into the side lobe, let's say that's, a watt of attenuation. It drops it low and it receives 0 watts. This is a simplification. This is all actually in dB, so it's all logarithmic scale, that kind of thing. But the same thing is going on here. So what I just said there is, if you transmit the same power level to the main beam or the side lobes, the main beam will be able to see it really, really well, and the side lobes will see a very degraded or lower power version. And this lets them localize and guarantee, in their eyes, that their target is where the main beam is looking. Well, if I wait for your main beam to scan over a bit, and these beams scan extremely quickly, nanosecond switching, very, very fast. So I don't have to wait very long. And let's say I put 2 watts in. Well, the main beam, who would have seen a watt, is now looking somewhere else. So the side lobes are seeing me. And we said the side lobes have 1 watt of attenuation, which means my 2 watts go in, and it sees 1 watt. So what does it think? It thinks where the main beam is looking, there's something there, but there isn't. Because we injected fake power into a side lobe. But we amped its amplitude, and that let us generate a fake target in its eyes at a different position in space. And you can do these all simultaneously. That's how it's really done. And also you can switch it up as you go pretty, pretty quickly. This one's the harder explanation. Does everyone kind of get it? Are there any questions? I'm willing to sit here and melon this for a bit, yeah.
So the main area that the radar is pointing has the strongest receive.
Yep.
I guess receive.
It has the strongest gain, right? Strongest antenna gain, strongest receive capability.
And then side has less. So after it hits a signal with the main beam, we want to send a larger pulse after to the side beam to kind of throw off.
To trick it.
Okay.
Because when it receives a strong signal, it will always expect that that was from the main beam location.
Okay.
So by injecting a strong signal into a side beam, we can create, because it'll be looking somewhere else when we do that.
Okay.
And in that moment, it'll say, oh, someone's over there, but I came in from this angle. But it has no way to discern that.
Okay.
And by the way, so that's 20 elements right there. I actually have this calculator up because I just want to demonstrate something real quick. Great website. If you ever need to visualize stuff, like for RF theory stuff, vnoth.org, great, I love this stuff. So, if we just do 5 elements real quick, very simple antenna pattern. And you'll notice as we go and increase the elements, this thing becomes more and more narrow. And keep in mind, this is a linear array, so it's just one dimension. If you made this a 2x2 array, it would have the same pattern just in 3-dimensional space. And when you have that, then you can steer it in 2 directions, and then by combining it, you can steer it anywhere in like that space, which is nice. So let's go up to 20 where we were for that figure I showed you. So okay, we're back where we expected. Keep in mind, so what we're looking at here, this is the main beam, and you can note that there's angles here. At 20 elements, this main beam is, I'd call it, 10 degrees wide maybe, that kind of thing. So that's our resolution, our angular resolution as we go through space. So if this is a linear array and it's 20, and then we made it into a 2x2, so 20 by 20, That's about 400 elements, right? Not about, it is 400 elements. Modern advanced radars have thousands of elements. So this one doesn't let me go beyond 100, it caps out. Let me kind of show you what an 100 looks like. Yeah, we start getting narrow. So 100 by 100, what's that? It's like 10,000? Yeah, that's a lot. Those exist, by the way, not on planes, but there are emplacements of radars, a lot of very fancy early warning radars that do have comical numbers of elements, and that's because they're looking like tens of thousands of kilometers into space type thing. Yeah.
So to make a convincing target like jam signal, do you need to know that pattern? Does the adversary need to know the pattern ahead of time?
For the most part, yeah. Or to select your power levels, you would want information about the pattern. Because there is a countermeasure to just blanket mass power, and that's automatic gain control. They'll catch that there's a problem, because again, as we know, the radar signal it sends out is strong, but after 2 bounces, or bouncing back, it becomes relatively weak. So they have a gain control. If you just try to jam things, it'll clip it. So you do want to know things like the receive pattern, because that will enable you to specifically set your amplitudes accordingly. And at the highest level, we get very precise with this, which means you need to have like very good intelligence. And that's the basis of a lot of these techniques is like extremely good supporting intelligence. So again, those electronic support measures are extremely vital to make these types of systems work very well. But yeah, so you get these laser, yeah, what's up?
I was gonna ask, what if you have multiple systems doing radar at the same time? What happens when they're like spaced apart?
It gets fancy. So, this is called a phased array antenna. It lets you steer the beam, as we've been saying. I can have a phased array antenna on myself. It doesn't have to be a radar. I can send my electronic jamming stuff, my target-like signals, through these steered antenna. Which means I have antenna, when the radar comes in on me, I have arrays that detect and localize, as in they find the incident angle onto me and say, radar's right there and there. Or we have intelligence ahead of time that says, hey, my GPS location is here, and we know that there are assets here and here, right? That kind of thing. You can do it either way. Often they do both. And then we can do things like steer our own beams to each asset. And by the way, this is a very useful thing. You see here, this is a single beam. That's not a hard rule. With a single phased array antenna, you're controlling each individual element on its own, which is why these are hilariously expensive. Like we're talking millions of dollars for a single antenna system sometimes, because you're controlling sometimes thousands of antennas simultaneously. But when you do this, you don't have to only generate one beam. You can generate multiple beams simultaneously and steer them all on their own. The math gets a bit fancier, but it can be done. And we do it all the time. So using that technique, you can target multiple people at once. And because you're controlling each antenna independently, including the signals on each antenna, that's the real expensive part, you can have different signatures in different directions to different radars. And then they're really confused, because guess what? The radars are talking to each other. Most modern radars are networked to try and agree with one another, which means now you're really messing with them, because they're all gonna be like, there's 200 people coming, and it could be like 2 guys. Because it just gets multiplicatively bad. It gets real fancy. Yeah. But, so that's just how this whole thing works with the amplitude. So, and the polarization stuff, which is one of the other methods, I'll briefly talk about polarization here. I'm not gonna try and explain in depth how you do polarization angle stuff. Okay, I'll do it a little bit. All right, so let me go back to viewing this. So I put this in here just in case everyone isn't super familiar with electromagnetic polarization. This figure is not great, but it's good enough. So I'm an antenna. Here's my antenna. This is a vertically positioned antenna. I put a radio wave on it, it oscillates, sends a signal out into the air. If I have another antenna downrange, and it's positioned like this, 90 degrees from me, I will receive little to no power, because the oscillation is not oscillating within the same plane as my receiver, my antenna. that's linear polarization, vertical, horizontal. If they're cross pole, and this is the important keyword we're gonna get here, cross polarization. If they're cross pole like this, generally, at least in mathematical terms, there should be no data or no information transfer here. In real life, you're never gonna be perfect. So it'll be a little bit, but it'll be hilariously low, often like 30, 40 dB less, which is massive. Just imagine, negative 3 dB is a 50% power reduction. So, negative 40 is like negative, like 99.99999% reduction, like super, super low. Circular polarization, kind of a superposition of linear and horizontal at the same time. That's why they kind of draw it like this. It's a bit more complicated than that, but we'll give it to them. In reality, circular polarization looks more like you have a linear pattern that as it traverses through space, it rotates about an axis as it's moving. Which means, technically, if you have a circularly polarized wave, either any intermittent, vertical, horizontal, and anywhere in between is generally able to receive a circularly polarized signal, although the power levels may be a bit lower because it's spreading its energy across multiple planes at the same time. And elliptical is just the non-perfect instance of circular, which just means that this guy and this guy's superposition aren't the same magnitude, so it ends up as an ellipse instead of a circle. Polarization is important, and what I just said there with my first thing is that a vertical antenna has a vertical polarization. When that wave, vertically polarized radio wave, hits a target, its polarization can change from the scattering effects. And when that happens, that's another way you can lose receive energy, is you could scatter to a couple different polarizations. So not only do you lose overall energy from travel, but if your receiver is not cross-pole and it's linear or horizontally polarized, you're gonna lose even more energy that way. But good news with polarization, if you have multiple radars operating on the same frequency, but different polarizations, they won't interfere with each other nearly as much. That's the same way we do a lot of communication with modern things. Same frequencies, but we swap polarizations, that kind of thing, so we don't interfere. If you have really, really finite or really, really precise equipment, you could basically have this polarization, this one, this one, this one, this one, and communicate simultaneously with those channels. It's not perfect, but it can be done. Is that something? So, this word I said is cross-pole. Well, radar antennae have an inherent polarization to them. So let's say you are a linear polarized antenna. You can introduce cross-pole jamming where I send signals at significant amplitudes, but weird polarizations, and it does the same type of thing that that amplitude stuff we mentioned does. It interacts with the radar and generates a weird high magnitude signal at a look angle it's not expecting. But instead of using purely amplitude to make that happen, you're using polarization as well. It gets a little fancy. If you Google, like go to YouTube and type in like cross-pole jamming, there's this dude out of Canada who has like this crazy sim suite. You've probably seen that thing. Yeah, he won't sell it to me, he's mean. But he has a much better explanation and demonstration of how cross-pole is useful. But the point of cross-pole jamming and polarization jamming broadly is to introduce angular variations, just like the other one. So as long as you know that, you understand that if you want to mess with their angle, you could use polarization as well as amplitude. So it's a good tool to have in the toolbox. And then multiple sources is just a combination of all these things. Again, a lot of this is playing with the antenna pattern. If they're looking somewhere else and signals are coming from various angles, you can mess with them because they're gonna think it's coming from there when it's actually just high noise or high false targets into their side lobes. Okay, so we've talked a lot about the ways to construct these signatures, what to play with from a signal perspective to introduce them, and how you can kind of like fine tune what you're trying to get. Now we're going to talk a bit more about how it's actually done from a hardware perspective. Let's take something going, 600 miles away. That's a super long range radar, right? 1,000 kilometers. As we said, this is light speed. The approximate bing bong speed is about 6 milliseconds. So that's your window to do something actively if you weren't already aware of what's going on. If you're trying to pick up an incident wave and catch it, manipulate it, and send it back, Your window is 6 milliseconds. So, in this time, first thing, you need to find the radar. As I said, you have an antenna array on yourself that can localize the radiation coming in on you, and you can catch it. When you do that, that's the first step. You do that first. Then, you identify what kind of signal it's emitting. It's extremely expensive to make your hardware capable of dealing with literally everything. So often, you have to have multiple modules that you can switch between depending on the signal you have to deal with. That introduces time, because you have to identify who you were looking for and then switch to that circuit. Then, you need to catch the signal, process it, do the manipulations we talked about, mess with the properties we care about messing with, and then play it back at a reasonable power level to the radar. When I say that reasonable power level thing, let's think about what that actually means. As I said, if you just blast a huge power level back, it's going to do automatic gain control and be like, okay, that's obviously not real. I should never get half a watt back from a reflection. It's just not physically possible, right? I didn't emit infinite energy towards them. How do you do that, though? What does it mean, reasonable power level? Well, you need to know where they are, where you are, and on the fly, do that wave propagation math. Incorporate your own antenna pattern to note, because if your antenna pattern's wider, it means the energy drops off more over distance. So based on that pattern, you have to compensate your power levels, all this fancy stuff. So you got to do a whole bunch of, really just a lot of trigonometry and then radar propagation math. Yeah.
Does that mean is there like a system in place then for like when you're, say you got the jet flying through the air, we already have like a mapped out, say, shape of the earth, and it's like, hey, we know there's something here, just expect this when you're flying through this area?
Are you saying if we have a map of the Earth, or we have like a map of all enemy adversary assets?
So if you have like a map kind of like of enemy adversary assets,
Yeah.
and is it just like the computer's like, oh, we're in this area, expect something from here with this much power? Or is it
So because we're catching, the wave will come in and hit us. We have an antenna that catches it, so we can measure on the spot the location, like the angle of attack it's coming from,
okay.
and we can measure its power level in.
Okay.
And then if, again, with really good electronic support measures, we'll have a fingerprint of that waveform, so we'll know that, hey, you know, what's the name of that Russian one? Yeah, they all have stupid names. That's NATO's fault. The Russians didn't name them, we named them. But regardless, all the radars have names. All these things have names. So we have fingerprint emissions. So a signal comes in from some angle, and we know our location, whether it's GPS or inertial. We're aware of our position in space. And then we can get that waveform and process it and compare it against our internal map of what assets we know in the region. We'll be like, oh, that's radar 3.
Okay.
And then you can deploy specific countermeasures or plans drawn up against radar 3. You don't always have electronic support measures. And often, a lot of military radars, specifically SAM, so surface-to-air missile systems, are designed for so-called scoot and shoot. And what that means is it's a mobile emplacement. They set up, they're scanning, they catch you, shoot their missile, and then in like 3 to 15 minutes, they pack up the whole thing and move. Why? Well, one, it's really hard to map if they're mobile. There's no way to know ahead of time where they'll be if they got wheels. So that's important for the ability to do the super fast processing and catching and localizing. Additionally, from their perspective, why are they shooting and scooting? Is it just to confuse us? No, it's because of those radiation missiles I mentioned earlier. Those missiles are designed predominantly to track radars. So they use their radar, see you, shoot you, pack it up immediately because we probably sent something to hit them. So they got to get out of there real fast. So that's a little bit of con ops there with that kind of thing. But this whole concept of what's necessary to be done here is an extremely complex operation, and most technology is just not capable of it, just not quick enough. This is where DRFM comes in, also known as digital radio frequency memory. If you Google digital radio frequency memory, you'll basically see, oh, this is for electronic warfare. It's basically a very specific type of system just for this. Also, anyone interested in electronic warfare, there's an association called the Association of Old Crows, whose expertise is in electronic countermeasures, electronic warfare systems. I think you are just allowed to join it if you're a U.S. citizen, that kind of deal. So, yeah, food for thought. But This is just like a surface level concept of DRFM. Real DRFM at the highest levels is a classified technology. If you go on things like IEEE Explore and look it up, you'll see papers of like, oh, here's this new architecture we're investigating, that kind of thing. But it's very rare that you'll just be able to Google this and like find like a product to buy, because this is very much a military asset. It's not exactly just for sale, nor are its technical specs just available. But the whole point of how this thing works though is a signal comes in, and in this case we see a down converter. And the point in our radio frequency world of a down converter or an up converter, they're just the opposite of one another. Let's say 10 gigahertz comes in. Well, in order to turn 10 gigahertz into bits, that means you have to sample it really fast because it's already moving fast. Everyone here know their Nyquist sampling? Nyquist theorem? Remind me, is it two times?
It is.
Okay, it's been a while since I took the class. But for Nyquist sampling, to prevent things like aliasing and other issues, you need to sample it at least 2 times the frequency. So if 10 gigs is coming in and you're directly sampling it, that's 20 gigahertz sampling. That exists. 20 gigasamples a second is a thing. It's just exceedingly expensive and bulky. So we don't like to do that. So things like radars, by the way, this is how most radios work. You have what's known as the carrier wave, let's call that the 10 gigahertz, and you have your data content. That's your coding, your chirps, whatever. The down converter drops your total frequency and you can shift it down to an intermediate frequency, which is why they call IF. And then immediately, once you get to this lower frequency, let's call it a couple hundred megahertz, that's pretty slow relatively. The digitizer, analog to digital converter, brings it into bits. Notice it's got RAM. We basically directly place this into random access memory, perform some computation and tweaks to it, combine it back up, reconstruct it. This is just the digital analog now. We send it back to analog, and then convert it back up to the high frequency and shoot it out. And this happens exceedingly quickly, nanosecond time spans, like faster than you could imagine. Like where your personal computer, clock frequency like 3 gigs, is doing a single instruction, this thing's done already. And it needs to be that quick because, 600 miles, I did this with this whole 6 millisecond thing. That's a really long engagement. That's very rare. Often you are far closer, so your time span's way worse, microseconds maybe. It could be pretty bad. So this is the whole concept here. I will note. I said earlier that they do this down convert, this up convert thing. This introduces problems because anytime you introduce a component in operation, it introduces noise. It introduces things like signal integrity issues. It'll change the waveform a bit. Every little change you introduce risks tipping the radar off that it's fake. So nowadays, we're starting to see things like direct sampling, where we don't even convert them anymore. We actually do put like 20 gigasample chips in there with the sole purpose of digitizing these waveforms as fast as possible with as little aliasing, signal integrity, any of that stuff, distortion, as little of that as possible. We try to reconstruct it perfectly coherently, as quickly as possible, and with as many sample points as possible. That's obviously extremely expensive, which is why these things are very expensive. Yeah. Any other questions on DRFM stuff?
Can you say what a typical bit resolution for the A to D would be in this kind? Is that a spec?
I think I can. Let me think to myself. I know it was on my unclass computer, so I think it's right. We'll say I've seen better than 8.
Mm-hmm.
I've seen better than 8. I won't say the best I've seen, but I've seen better than 8 at like 20 gigas, like ridiculous speeds.
Mm-hmm.
So pretty good, pretty significant. But obviously, as we're aware here, that these levels are rather small and they can get pretty precise. So they do need a lot of bits to reconstruct them accurately. We did that one already. Okay. Yeah, we're pushing towards the end here. So this right here is one of my favorite systems ever made. This is the ADM, specifically this is the ADM 160, there's a bunch of variants. MALD stands for Miniature Air-Launched Decoy. Basically, he's a tiny little cruise missile, but he doesn't have a bomb in him. This guy's whole purpose in life is to deceive air defense systems. And I think we can load like a bunch of them on a single jet. Like, it's really ridiculous. There's a video actually recently. This asset used to be like, no one even knew what it was type thing. Like, no one even said its name. It was all locked up behind TS, all that kind of stuff, top secret. But one of the first known field uses publicly released was that we gave them to Ukraine, and a lot of their early success with taking out Russian SAM sites was because we were basically lending them these. And by lending, it means they were lost, but it's, that's the point. There are some pictures, if you Google the MALD, you'll find pictures of the wreckage of them from Ukraine. And then there was an advertisement for the Ukrainian Air Force, where the guy was literally talking about it and sitting next to the MALD on their plane. So they are very much publicly in use, and one of the reasons that the Ukrainians have been so successful in like penetrating deeper into Russian contested zones is because of these systems. If you don't have high-end jamming capability, you're gonna get shut down. The Ukrainians don't have 5th-gen stealth fighters. They can be seen from miles and miles away, and even old Russian systems can absolutely shoot them down. So, the MALD is awesome, and it has an advanced suite of sensors and computation, and it can create false RCS signatures that look like different assets. This thing has a whole bunch of different things it can simulate, and it can simulate a whole bunch of targets at once. It's very fancy. And there's a variant called the MALD J, which instead of just faking signatures, can also actively do specific types of jamming.
Excuse me.
Yes.
Did I miss, what is RCS?
Sorry, RCS is the abbreviation for radar cross-section. That's what I didn't say it. I'll say it here, just so everyone's aware, since I've been saying it quite a lot. Radar cross-section is a unit of measurement, generally either expressed in square meters, or those in the know, the most common unit is decibels per square meter, relative to 1 meter squared, that kind of thing. Radar cross-section is basically a measurement of how large a target is, and it's the strength of its radar return, the reflected energy back. As we know, as the radar sends energy out, it goes with the whole inverse square law, so it's spreading out. So if a target is, let's say, 1 square meter, it's just a flat perpendicular panel 1 square meter from the radar, there's some amount of energy if the cross-section of 1 square meter will hit it and then come back. And that's gonna be some magnitude. Well, what happens if it's 10 square meters? A larger cross-section hits it and comes back, which means the strength of the energy returning is increased. Larger radar cross-section, higher magnitude return, often means a couple things. You compare it with your time of flight to discern if it's just really, really close to you, because again, it's a cross-section deal. But assuming it's not super close to you, and you have 2 targets, one has a far higher magnitude than the other, and they're the same distance away, you can basically guarantee, minus us messing with you, that the target with the higher magnitude is a physically larger structure, right? So a commercial airliner is gonna have like 100 square meter, cross-section, massive plane with no stealth features whatsoever. Whereas like a B-2 bomber could be like 0.001 blah, blah, blah meters. Super tiny, smaller than a bumblebee type thing. Even though they're physically comparable sizes, and that's because of stealth features. Yeah.
Share a question for that thing. Does that like shoot out and then come back?
Nah.
No, that's just,
Oh, it's gone, yeah.
okay.
Yeah, it's gone. Yeah, whenever you have assets like this with like real fancy hardware inside, once their mission's done, they just, they just pop.
Okay.
So they can't just
Self-destruct?
Huh?
They self-destruct?
Yeah. You don't want them to just get that thing. Because the big thing isn't even really the hardware. Like, anyone really in the game knows technically like what they're doing here. Now, we may have fancier chips or something at play that they might not be able to get. But the real important thing is, as mentioned, they have an internal memory of a lot of ESM stuff that we've collected. So generally, you don't want your enemy to know what features and systems and you've collected on, because particularly when it comes to things like this, like RCS signatures, it's very easy to change a vehicle's RCS signature. Whenever you see, let's say, an F-35 at an air show, they probably, almost always, have an RCS augmentation device on board. And really all that looks like is a fancy bike reflector. They normally put these little nubs on the wings or on the body. Do you guys know what a bike reflector's operating principle is? It's a corner reflector is the proper term. What a corner reflector is let's say I take a cube, so it's a flat cube right here. Let's say I turn it so a point of the cube, a vertex, is perfectly aiming at you and perfectly aiming at me. Slice it in half around the side, down the side vertexes. So now it's kind of like a pyramid shape. But the concave section is like looking at you guys. So here's my corner reflector, that's the structure. Bike reflectors have hundreds of very, very tiny mirror reflective ones. That's their shape. That's what that pattern looks like. If light comes in, or in this case radar, it's just metal, comes in at this angle, it hits, bounces, and goes back. Corner reflectors guarantee that an incident wave goes back the way it came. Why do we use them on bikes? So any light from any angle reflects back to the sender, so you're highly visible at night. Same principles as radar. Any enemy radar trying to be sneaky at our air show, getting data on our assets for their ECM systems, they're not going to get anything useful because they're just going to get this big blob of massive radar cross-section because we put a bunch of corner reflectors on our vehicle. So it's very easy to change these things RCS. It doesn't take much, particularly if it's already a stealthy platform. Its radar cross-section is already smaller than a single human. You don't need to do much to change it. You could literally put a bolt on it and it would look way bigger on radar. You can do a bunch of tricks. On the YouTube channel where we have all the recorded talks, I have several talks on stealth concepts that go into more depth on that, if the whole stealth and radar cross-section stuff does interest you guys. But yeah, so that's the end of most of the content. We can do like an open Q&A and I'll flip over. Yeah, what's up?
Do you think you could go back 2 or 3 slides to where you had that right
Yeah.
there, the DRFM? So, what is the purpose of that? Well, for one, am I to interpret this device as being just to process the information you get from a radar very quickly, or is this part of the target, like measure a signal really quick and send it back in some spoofed manner?
A DRFM specifically is for very rapidly catching an enemy signal, reconstructing, manipulating, and sending it back out.
Okay.
Yeah,
Can you elaborate on what that sampling frequency generator is for? Is that like the?
Yeah. So you see there's the local oscillator at the top, and that's just like a standard radio component for a converter. The sampling frequency generator is just, so I said, let's say you have a 10 gig signal, it's a direct sample, that kind of thing. The sampling frequency generator is generating the clock at that 2 times frequency necessary to do that direct slicing.
Oh.
So the sampling frequency generator just determines your slicing frequency or your sampling.
Oscillator is to lower the frequency down to something you can measure more easily. And
Yeah. So
the
like,
generator is just basically the clock of your computer that you're using to
real fancy.
process the data.
Yeah, and these types of like sample frequency generators, like let's say you just have a really high-end oscilloscope, you can purchase like commercial Keysight, Agilent, what have you, oscopes that have like 20, 40 gigasamples. They do exist. They cost more than your house, but they do exist. So locally, one of the reasons these things get expensive when you go up to higher frequencies is because precision is a requirement at higher frequencies. It becomes precise and specialized. So those things have sample frequency generators inside or signal synthesizers, whatever they need to generate the super fast clock signals to trip the sample points as they go.
And you said those are in the 10s or 20s or more of gigahertz?
Depends what you're up against, but yes. The most common, so I mentioned this word earlier, I didn't get any questions on it, but since we're in the Q&A phase, I'll just do some specificity on it. There are things called early warning radars, and there are things called fire control quality or engagement radars. So there's basically 2 types. Early warning radars are low frequency, on the order of maybe hundreds of megahertz, or potentially even lower. The point of an early warning radar is these low frequency waves are very minimally attenuated by free space, so they propagate really, really well. And they have this fancy property of, 1, not being absorbed by the ground easily. They can hit the ground and travel along it. And here's the best one, over the horizon. You can aim it up, bounce it off the ionosphere, and it reflects back down and you can see past the curvature of the Earth. Certain systems can see around the entire Earth. Yeah, the Russian one did that. That was a bad design. Woodpecker, it's called Woodpecker. Yeah. Back in like the Cold War, the Russians had this massive early warning array called.
Those giant,
Yes, these giant pylons.
that are like the size of a football field across.
And the reason it has to be that is because your antenna is generally resonant to the wavelength, lower frequency, generally means larger wavelength. And what that means is most antenna often you're going to target like half wavelength. If I told you 300 megahertz is a 1 meter wavelength, if you're down at like 50 meg or something, your antenna's gonna be like 10 meters or some crazy amount. Like they start getting huge. So that's why the woodpeckers are these massive things. So the woodpecker generated this ridiculous pulse that would traverse the whole planet in a loop a couple times. It was just stupid. Like it's just like, why are we even doing this? But yeah, it was bad because a lot of like communication frequencies use that. So like you'd be talking and then you'd just like just jam. That's stupid. But so over the horizon systems are large wavelength and they can bounce around the Earth and see you crazy far away. Obviously, if you're seeing around the Earth, we can understand that that's a massive distance. However, larger wavelength means poor resolution. Their ability to localize you is really bad. Their accuracy is poor. They'll know you're there, but the best they can say is like, he's probably within this 5-mile radius-ish. Generally, it's a little less now, but still, it's not great at localizing you precisely, and absolutely not precisely enough to fire upon you. You need tracks that are so-called engagement quality or fire control quality. That's where your proper microwave region things come into play. S-band, which is 2 to 4 gigahertz, and X-band, 8 to 12 gigahertz. These are the most common fire control quality radars out there. These are so-called line of sight. They attenuate in the air pretty bad, so you need higher power levels to go to certain ranges. They do not reflect off the ionosphere. They do not travel along the Earth. So you can only really get a line of sight track on them. You can't get any of these other fancy features. But their resolution is crazy. We're talking like sometimes you can even get like sub-centimeter resolutions. Like you basically just know where they are. And that's why they're necessary in order to inform a missile where to go. Or an interceptor, whatever, in the plane. But yeah, so when you hear like FCQ, that's fire control quality. When you hear engagement radar, just think higher frequency systems, and early warning or warning radars, think lower frequency system. And by the way, when you do the math for something's radar cross-section, there's formulas for it. The larger wavelength at play, the larger your radar cross-section is. Which means if you're really, really fancy and you make your radar cross-section super, super tiny, that's only at a specific frequency. So things like these early warning radars are very valuable against high-end stealth platforms because it doesn't matter how stealthy you are, if you get hit by like a 2 megahertz wave, whose wavelength is like, 300 meters or something, they'll actually see you pretty handily. But again, their precision's like, oh, he's maybe like this 10-mile radius maybe. So again, they can't shoot on you, but they'll be aware you're coming. So that's why it's really great to just jam those out. Not even with false target, because remember the whole thing I mentioned is an antenna needs to be comparable to the frequency of play based on wavelength. So these super low wavelengths, you just have to jam them with these large platforms from a distance with just barrage jamming. You're not going to be able to do really good target-like jamming because the system necessary to generate that signal would need antennas that are just massive. Yeah.
How far can you be to jam those?
Depends on how much power you want to dump, realistically, and how directive your array is. Again, since the antennas are huge here, it's actually very hard to make directive antenna arrays. That whole thing we were talking about earlier with like 100, 1,000 elements, these are at high frequencies where the antennas are like this big. So it's rather simple to pack a bunch into an area. Once you get to like a meter or more wavelength, arrays look like football fields. So the actual answer is you'll probably just have like a large parabolic dish and just kind of blast in that general region with like a lot of power, like maybe even hundreds of watts, just to block something out.
Okay.
Any other questions? Yeah.
So decoys are used in ICBMs usually. Right? Decoys are used in ICBMs usually, and are there ways for them to distinguish decoys from real incoming warheads?
I'm not allowed to answer that one, unfortunately. But if you Google Minuteman 3 and Peacekeeper stuff, you should be able to get a good idea of that. The Minuteman 3 and the Peacekeeper ICBM system are very majority unclassified nowadays. They've released and declassified quite a lot of reports. If you dig deep enough into some of the Peacekeeper stuff, you'll be able to find what you want. So, you're hooked, you want to learn more, what we got? Well, At UAH, we've got some classes. Fortunately, it's all electrical engineering. That's my gig. I don't know if it's your gig. But obviously, a lot of the stuff we've said here has specific requirements. We've talked a lot about antennas. We talked a lot about radars. We talked about signal processing and things like that. And obviously, a lot of this is done purely digitally nowadays. So obviously, any understanding of signal processing and like a lot of like high performance computing stuff and computer architecture like that also helps. But broadly, my opinion, antenna design and analysis, fundamentals of radar systems, radar tracking, radar waveforms and signal processing, that's a big one. All these courses are rather helpful if you're like, oh, I want to be a radar SME, subject matter expert. Now, this is my gig now, right? Again, I recommend Radar Electronic Warfare by August Golden Jr., but these topics are rather popular in literature because if you're an academic, it's really easy to get funding from the government. So if you do stuff that the government likes, you are probably better suited to get contracts, grants, what have you. So going on to places like IEEE Explore, which is a paid journal, but UH gets all of you guys as students access to these journals for free. You can access it through the Salmon Library's website. You just click the Journals and Publications section and go to IEEE Explore and log in through the UH portal, and you'll be given access to 7.2 million articles, a lot of which talk about stuff like this. It's a great way to stay on the cusp of the newest stuff and also get a really good theoretical understanding of some of the older stuff. But you gotta learn how to read research papers. It's a skill in itself, right? But in my opinion, it's a worthwhile one to build. These types of fields, a lot of the stuff we focus on, because we are in Huntsville, so a lot of the expertise I can get, including my own, happens to be Department of Defense adjacent. There's a lot of fields in science and engineering that are really, really important to modern defense technology, dual use things, because a lot of stuff that we develop for defense is very often also used in the future or at the same time in the commercial sectors. The internet, a lot of modern communication schemes. Just because radar is very useful for things like weapons doesn't mean it's not useful for things like tracking weather, tracking massive movements in global features like salinity of the oceans, that kind of stuff. We have hundreds of satellites whose sole purpose is to do very precise measurements of the Earth's climate, all that kind of stuff using synthetic aperture radars. So these are all things you can do on the commercial or government defense side. But if you want to really get into this stuff at the highest level, it's almost always tied up behind classified barriers, because at the highest level, often a commercial application doesn't need some ridiculous performance, but a classified one does. So if you are interested, go get a job over there so they'll get you a clearance. You can start getting in there. But often, yeah, it's going to end up being the Department of Defense if you are interested in a lot of these things. Specifically electronic warfare, there's just straight up no like commercial application of this. It's literally just jamming. So like, if you want to do this type of stuff, it's a very lucrative career. There's quite a lot going on here. It's only growing, but it is going to be tied up behind a vault door. So no phones allowed type thing. Yep, my references for here. The main book, again, Radar Electronic Warfare, but I list some other ones here. Anti-jamming techniques, if you're trying to avoid being jammed, there's a whole bunch of those. More electronic warfare stuff. Electronic intelligence is a big one, which is, again, like the concepts of intercepting and manipulating stuff. And then electronic warfare and radar systems engineering handbook. This one's great. It's a hard thing to get your copy of physically. You can find it online through like GTA Mill, that kind of thing. But the Naval Air Command makes this really nice thing. My boss gave it to me back in the day. And it's just this nice big hand guide to just really rapidly give you all the little bits you need to know. It's designed to spin up officers on electronic warfare and radar techniques. Yeah.
I have more questions about the DR, I think.
Okay.
You can go back. So, you maybe can't answer this. What's like the highest, I guess, frequency that these things can be built to discern, I guess? Like, are they only in the like high microwaves, or do they get down to like far infrared?
There are definitely limits to how low they get, just because of physical antenna limitations. So often, though, if you're going to talk something like this, generally, the lower frequencies for practical use is similar to a lot of commercial SDRs. So lowest, you're looking somewhere like 1 to 2, 3 megahertz.
Okay,
highest,
I meant highest.
yeah, highest. We'll just go with like one of the fastest commercial O-scope speeds for that, so about 40.
Okay,
40
so-
gigasamples means 20 gigahertz.
So is there any kind of like far infrared or
So-
equivalent that uses, instead of an antenna, some kind of,
Yes,
photo
so
array.
yeah, when you get to optical region stuff, it's a similar process, but it's a different ball game. Antennas no longer work the same
Yeah.
way when you start talking about light. It's still an electromagnetic wave, yes, but if you just put a metal rod up in the air, there are effects at play. Einstein's proven some electricity generation from photon, that kind of thing. But still, generally, you're not going to get what you expect. It's going to be a lot of optical trains. So IRST systems, infrared search and track, these types of things, they can be jammed with so-called infrared pods. So there are several systems that we employ to defend large, slow assets. And they're basically just pods you place on the back. And imagine as like a laser turret where it tracks something and says, oh, there's an infrared sensor, and then just flicks an infrared at it, either tries to fry it out or just block it out. To my knowledge, I have never heard of a target-like optical jamming. That would require some ridiculous stuff. If it exists, that's cool, but I've never seen it.
and one more question, and I'll
Yeah.
stop. So, is there like absolutely no sort of consumer way, like is there any way the average person could get their hands on?
Probably not a DRFM specifically, but you could build one technically, because it is rather simple in its actual implementation here. It's just take the RF signal, sample it fast, and obviously the reason they use RAM here is just because they need to be able to do fast memory operations. Manipulate it quickly, either in RAM and cache, whatever you want to do, and then put it back to a signal, spit it out. Technically, all that means for you is you buy a very fast ADC, and often the ADC and the DAC are the same chip. They can do either. So you buy one chip for that. Let's say you wanted to do like 5 gigahertz or 5 gigasamples, or let's say 10 gigasamples. That chip alone's like $1,200 on Mauser, and there's faster. But so you've super fast ADC, you got that. RAM, bad time to buy RAM, but yeah, get your RAM, and then microcontroller with a DRM. Sorry, not DRM. DMA, direct memory access controller. That's what you want. Very fast memory operations. So technically, that's it. It's just those 3 parts. In reality, though, unfortunately for you, you can't actually just stick an antenna onto an ADC and expect it to just sample it out. You're going to have to do some other stuff. So there's probably some other requisite RF components, amplifiers, LNAs, low noise amplifiers, buffers, what have you, that you're going to need in order to set the signals up to be sampled. Those could be expensive depending on the frequency. High frequency equals high money. Very high expensive.
Frequency equals high money.
High money. But yeah, the answer is you can build it. And funny enough, the government doesn't necessarily like people doing stuff like this, but at the same time, this is how new companies are founded, particularly in defense. A lot of advanced defense technology that maybe 10, 20 years ago would have been unthinkable for a civilian to ever even come close to in terms of building it. You can absolutely just do in your bedroom in maybe a couple weeks. Most guided missiles are easy. It's rather simple nowadays and not that expensive. Obviously, if it needs to go far and fast, you're just spending a lot of money on rocket fuel at that point. But actual missile guidance is not that complicated, and AIAA has entire textbooks on it, straight up, public release. So it's not that bad. Radars, as he said earlier, automotive radars exist. There's a lot of very nice, very fancy radar modules that can do some very impressive stuff. Texas Instruments sells radar modules that can even physically track you. And the radars are phased arrays, but they use this fancy synthetic signal processing. I saw it at a conference last year, which was really impressive. They could track 6 targets simultaneously, 79 gigahertz. Chip was this big, all integrated onto one wafer. It was nuts. And that chip was $50. You could just buy that. Now you're gonna have to spend $200 on the processor it hooks up to, or build your own. But yeah, there's a lot of capabilities that are there. And again, you could take that radar chip that I just said, slap it in the front of a missile. You're set, right? Yeah.
2 things. What does AIAA mean?
AIAA is the American Institute of Aeronautics Astronautics Engineers. It's your air. So where IEEE is electrical computer, AIAA is aeromechy, basically.
Okay. And the next one is, how many of those would be on like an aircraft, generally speaking? Like, in order, if it's supposed to receive a signal,
Yeah.
and like, are there just numerous ones just peppered throughout the plane?
The answer is, in reality, you'd probably only have like one of these for an asset, because the one they would have is so comically fast that it can do everything that needs to be done at once.
Okay.
And when you combine this type of thing with stealth design, other Blue Force assets assisting you with other things like they're jamming out other people, that kind of stuff, you can really make it where your mission is extremely defined and you know exactly what's going on. You have a bunch of other guys jamming out radars you don't want to deal with, so you can focus him on the most important asset. But, yeah, I think that's it. And there's our sign-on. Yeah. So, okay. Blue Force, yes. So in the know, when you're talking like ops design, like concept of operations, how are you going to design a mission set, threat set, that kind of thing. There's the concept of Blue Force assets, Red Force assets. Blue Force is your friendly team, Red Force is your adversary team. It's like a video game.
How convenient.
Yeah. Yeah, it's very, that's a whole career in itself, actually. You can have your entire job can literally be, they feed you intelligence data on Red Force stuff and our own stuff, and your job is to mission plan. Come up with different ways to beat things. Cool, it's very fun. It's like threat engineering, I think. I've met a couple of those guys. Weird dude, no. Cool guys. Yeah.
What about cell phone jamming?
Cell phone jamming.
Yeah, as a commercial.
You could do it. It's illegal, but you can absolutely do it. So cell phones, ironically, are rather easy to jam. If you were to try and measure the cell phone signal coming out of your phone, obviously all of our phones are operating at the same time right now with very high throughput data rates. And the way they do that is they have actually a pretty impressive amount of frequency agility. So within their allowed band, they're jumping around a lot to prevent collisions and jamming each other. But the band, like they might have very precise and narrow buckets where they can jump around in. But unfortunately, the overall band of where they're all communicating is rather small. So it's fairly simple to barrage jam just that spot and just block out all the phones. So if you do go to places like DC frequently, let's just say motorcades come with cell phone jammers. So if you're in DC in the right place at the right time, your phone will lose service.
Yeah, but are there commercial cell phone jammers like
Oh, absolutely.
for high schools or, you know?
Unfortunately, actually, I think that's a real thing. I think I know about that. They have, in fact, built commercial jammers to try and jam phones so students are disincentivized to use them. I think it's still illegal. I don't think it's legal because jamming cell phone signals also blocks 911 and among other emergency services. So I don't think it's legal. But just because something's illegal doesn't mean it's not available on Amazon. So, and funny enough, legally, you are perfectly allowed to own a jammer in this country. There is no law against that. The law is against illegal or illicit interference. So you can have as many jammers as you want, you just can't turn them on. Another caveat, technically the law doesn't say don't turn them on, it says don't interfere. So if you are forward thinking and you build a Faraday cage in your home, you can do whatever you want. In my garage, I have a Faraday cage so I can do whatever I want. It's actually better than a Faraday cage. It is a shielded RF enclosure with $2,500 of RAM in it. RAM being radar absorbent material, yeah.
How big is your Faraday cage?
4.5 feet, 3.5 feet. So 3.5 foot square, 4.5 foot range. The dimensions of it were selected for the far field region of the radars I use. Because I do my own radar stuff. With modern software defined radios, you can actually kind of just do whatever you want. You pay like $300, $200 for like a hack RF, 1 meg to 6 gig. You can do quite a lot in there. And you can make it be a radar, you can make it be a jammer, you can make it be like just a normal radio, or really whatever you want. You control them with software. You're at C++ code.
When you said far field region,
Mhm.
But you're saying that the room is only like a meter?
A little over a meter. Yeah, the frequencies I use are rather high.
Okay.
So far field region, let me see if I remember the equation. It's not super complicated. I think it's like, I thought it was like 2d squared over wavelength, I think. Something like that for the far field region. D being the largest dimension of your antenna. So that can matter if you do fancy stuff with arrays. But if you're using like single elements or that kind of stuff, or if you just use high frequencies means this gets smaller, and this can also technically get smaller, except he's scaling faster. It's a balancing equation, but basically generally higher frequency means far field compresses in.
When you say far field too, do you kind of just mean that that's where your radar operates as a radar?
Yes, so there's 3 regions. There's the near field. Fresnel is this middle region. Basically, when I say far field, what that actually means is the plane wave region. When you're really, really close, so obviously electromagnetic waves are comprised of 2 parts, electromagnetic, right? There's no such thing as a purely magnetic or a purely electric wave. They should generally have the other component, but there are times where one is dominant and one is not. Magnetic effects drop off faster than electric field effects, at least when it comes to propagation in free space. So magnetic is generally near field. You'd expect a magnetic force, like let's say you just had like a magnetic loop and you're sending current through it. That is like rather strong, super up close. But as you fly, go away, it drops off rather fast. Whereas the electric field generated can propagate farther generally. And at least for our purposes, almost all radar, not even almost, any radar is operating in the far field where it's just an electromagnetic plane wave. We're really focused on E field. H field, magnetic field, is a close near field situation. E field is a far field situation. And the Fresnel is as it's transitioning between them. It's more complicated than that, but ultimately, far field just means it's a plane wave now, so you can kind of get rid of like, does the wave have geometry anymore? You can just kind of treat it like a flat plane moving towards you. Way simpler for simulations and calculations. And it's practically true. Once you get past that far field, it's kind of flat enough. You're just like, yeah, whatever.
Because up until then, isn't it a spatial Fourier transform?
Probably, I don't know. I would assume maybe.
I don't know. I remember that being thrown around once.
I would assume. The Fresnel region, it gets wacky. I will note, with modern technology, you can basically make your radar do whatever you want. Like, you can do fancy stuff with antennas. I've seen people make like these ultra-wide bandwidth Vivaldi arrays. There's a type of antenna called a Vivaldi antenna, and it basically just looks like this. And like this is the conductor edge. And this lets you have different resonant spaces that match the different wavelengths, which means it's a broadband antenna. Fancy. I visited a site in Texas for a company, and they had a custom Vivaldi array with like 200 elements that was able to do like far field measurements, like a centimeter from something, at like almost any frequency. It was ridiculous. But you can calibrate for these effects. Like if you're willing to sit there and calibrate for everything, you can account for it. I'm not willing to do that, so I built my box a little bigger. But
other than just for playing around, what's the use of having a radar that can
do close stuff.
discriminate that closely? I mean, is it at
It's
that
a
point?
measurement tool for your own uses. There are very fancy hyper near field radars, and we use them to analyze stealth coding performance. So when you coat a plane or a stealth vehicle, whatever, a missile, you coat it in its stealth material and you do a bunch of other fancy stuff with it. They sell these fancy radar systems on robot arms that you could build, set up next to the thing, and it just gets real up close and just scans its surface. And it can give you these,
Depending on the wavelength.
yeah, so it can give you these crazy wideband responses, just like right up next to it though. It's really fancy. So no radar range needed. It's a really big improvement for maintenance. Stealth maintenance is hard. So it's nice to be able to do that without having to drag the whole thing into a radar chamber to do a full measurement. Those are very expensive. But yeah, if you're willing to calibrate, my chamber is keyed to like, I think my minimum is a gig. That's as low as I can go without going into the near field or the Fresnel region. And for me, that's fine. I don't want to go anywhere lower than that because a lot of my stuff I do is mobile platforms, a lot of drones, stuff like that. So I can't carry large antennas anyways, so I'm limited. A lot of the stuff I do, I put myself around 6, like C-band, 6 gigahertz. I personally don't have the money to go up to X-band quite yet. I'm working on it, but it's hard to make microwave sources. I have a home lab full of YIG oscillators. Those aren't going to go on a drone.
Oscillators?
YIG, it's a yttrium iron garnet oscillator. RF is magic, legit. But let me show you guys this. It's really cool, actually. We still use these a lot. Okay, oh, there we go. I would like to know about the oscillator, though. So this is the material. It's just a synthetic material. All right, bro. Let's try this. There you go. Yeah, YIG sphere. There we go. This is basically how it works. You control the resonance of the crystal with a magnetic field, and then this allows you to tune an RF oscillator. So some YIG systems can go all the way up to like 50 gig. So this is like the original, or one of the original compact high frequency signal generators that have a really high Q factor. They're high quality. They're spectrally pure. They're nice. It's just they're annoying because they're basically big cubes of steel. So I have a lot of them for like lab bench testing, because go ahead and try to find like broadband 10, 20 gigahertz signal generators. You're going to be spending thousands of dollars. Where you can go on eBay and get like used YIG oscillators from old test equipment for like $50. You just need to know how to control them. It's not that complicated, but you can do it with an Arduino. It's a good project. But yeah, these are really cool, and it's a good way to get cheap, high fidelity, and they're also rather high power, like -10 dBm, so less than a milliwatt, but from an RF perspective, that's pretty significant. So pretty nice. Yeah. I have a 26.5 gig YIG oscillator coming in on Saturday. Only $100, it's a good deal. Good deal. But yeah, these things are wacky. Yeah. Fun. Also, just one last thing, just to torment you guys. I love showing students this just in case they don't know. Who said you needed anything but just strips of metal to do anything? So when you get to like really high frequency fancy stuff, so like you guys are all familiar with the concept of filters, use like resistors, capacitors, inductors, whatever, to implement these filters. You can get real fancy with it. Well, what if I told you at high frequencies you can actually just make like fancy shapes of PCB metal and it works perfectly fine? So this is called a butterfly stub filter. This is a low pass filter. This is the art of analog RF equipment. If you go on eBay and you buy a bunch of old RF equipment and you open it up, you just get to see a bunch of this magic. And it's really cool. But legitimately, like, just know modern PCB manufacturing is dirt cheap. We're talking you can get 5 boards to your house in a week for like $3, not even trolling. That's just the actual price. It's completely free to design this. You go download a free PCB software and just draw some shapes. So as long as you know how to do it, you can do some really cool stuff. So just some food for thought. But yeah, so
There's some good 20-minute tutorials out there.
for KiCad or for doing filters like